Usually when you open up an app on your phone, there's this expectation of immediate perfection. Like you tap a button, a car shows up.
Right, yeah.
You swipe, and a 4K movie just instantly starts streaming. But when you actually peek behind the curtain of modern computer systems,
Oh, it's terrifying.
it is. When you look at how these distributed networks are actually glued together, that illusion of perfection completely vanishes. You realize you're looking at a landscape of, well, organized chaos.
It really is a digital high-wire act. I mean, we're talking about hundreds of microservices scattered across different global data centers, all basically screaming at each other simultaneously.
And over networks that are inherently unreliable.
Exactly.
So welcome to today's deep dive. We've got our hands on a really fascinating architectural blueprint today that essentially tries to police this chaos. It's a design document detailing the invisible contracts APIs that keep the internet from collapsing.
Which is quite a job.
Yeah, to say the least. And it pits two heavyweight design philosophies, RPC and REST, against each other. And we're going to see how these theories survive when they're put to the ultimate stress test, which in this document is a high-stakes, real-time AI platform.
Which honestly is the perfect environment to study this. Because if you're building a massive distributed system today, your biggest bottleneck isn't usually the code itself.
Right.
It's the communication layer. If you get the API contracts wrong, the whole architecture just falls apart.
Totally. Now, we all know the classic API analogy, right? It's the restaurant menu. The menu is the contract between you, the diner, and the kitchen. You use the menu to order, and it provides complete encapsulation.
Yeah, you don't need to see how the sausage is made.
Exactly. You don't have to see the grease fire in the back, and the chef can change out the ovens without having to teach you a whole new way to order a burger. But this blueprint takes that encapsulation a lot further, starting with, well, who actually gets to read the menu in the first place?
Right, because before you even decide on your protocols, you have to define the security perimeter. The document outlines three distinct tiers here. First, you have public APIs.
Which are just out there.
Fully exposed to the hostility of the open internet. So that means you are dealing with malicious actors, DDoS attacks, aggressive scraping, all of it.
Wow.
So you need incredibly strict rate limiting and user registration just to meter the usage.
Right, which is completely different from private or internal APIs where the data never actually leaves the company's internal network.
Exactly. For internal, you're basically just letting isolated engineering teams build on top of each other's services without, constantly stepping on each other's toes.
And then there's a middle ground, which I thought was really interesting. Partner APIs.
Yeah, those are exposed externally, but strictly to entities with formal legal business agreements.
So it's like a hybrid. It requires the heavy security of a public API, but the specialized, deep integration of an internal one.
Spot on. So once you've established who's allowed in the building, the document lays out 6 foundational pillars for building these contracts. You've got complete encapsulation, which we just touched on, ease of use.
Yeah.
Pagination.
So you don't crash a mobile app by sending back like a million database rows all at once.
Right, exactly. Then asynchronous operations, so the client isn't just hanging there frozen while a heavy background job runs. Versioning to ensure backwards compatibility. And then idempotency.
Okay, I want to spend a minute here because it's a massive concept. Simply put, an idempotent operation means that whether you perform it once or you perform it 10 times, the end state of the system is exactly the same.
It's arguably the most critical defensive concept in distributed systems.
But here's what I don't get. Why would a client be firing off the exact same critical request multiple times to begin with? I mean, that sounds like a bug.
Well, think about the physical real world.
Yeah.
Imagine you're on a subway, right?
Yeah.
You hit submit payment on your banking app just as the train enters a tunnel. The signal drops. Your phone's network layer has no idea what just happened, and it's programmed to be aggressive. So the second you catch a bar of 5G again, it just retries that payment request.
Oh, man. Okay, so if the system isn't idempotent, that blind retry might end up charging me twice.
It's a classic race condition. Because if your original request actually did make it to the bank's server, but only the confirmation got lost in the tunnel.
And the bank thinks I want to send that money again.
Exactly. A blind second request processes a second payment. So idempotency protects against this exact network unreliability. An idempotent API forces the client to generate a unique request ID.
So when the retry hits the server
checks the ID, sees it already processed that exact transaction, and just hands back the cached success confirmation without moving any more money.
That's a brilliant safeguard. And it perfectly sets up the underlying problem that engineers face here, which is that the network is fundamentally hostile and unstable. So how do we actually build the communication pipes over it? The first architectural style we're looking at tries a very specific, almost psychological trick on developers. It tries to pretend the network doesn't even exist. Enter RPC.
Remote procedure call.
Right.
RPC is entirely focused on what's called location transparency. The whole philosophy here is that a remote network call should look, feel, and behave exactly like a local function call within the developer's own code base.
So if I'm writing code to process an image, I just type process image in my editor. I don't care if that image is being processed by the CPU on my laptop or if it's being shipped off to a massive server farm in another country. It just runs.
Exactly. It hides all the plumbing.
To me, that sounds like a universal TV remote. I push a button in my hand and the action happens over inside the television, but it feels completely seamless on my end.
The remote analogy gets you halfway there, but there's a major catch. A TV remote is fire and forget. It just blasts an infrared signal and assumes the TV caught it. RPC is a two-way street. It expects an execution and a return value. And to make that illusion seamless, RPC relies on something called an IDL, an interface description language.
Yeah, the blueprint goes deep on this. The IDL is basically a single centralized file where you define all your endpoints and your data structures, right? And from that file, the system compiles what it calls stubs for both ends of the pipe.
Yes, exactly. The compiler generates a client stub and a server stub. So when you call that process image function, you're actually just calling the client stub locally.
Okay.
The stub intercepts the call, takes your data, and performs what we call marshalling. It serializes your local variables into network packets, handles all the messy TCP routing, fires it across the internet, and just waits.
And on the other end, the server stub catches it, unmarshals the packets back into variables, feeds it to the business logic, and then reverses the whole process to send the result back.
Exactly. But this brings us to the flaw in the illusion, which the document accurately labels the uncertainty problem.
Because you can't actually pretend the network isn't there forever. Going back to my remote, if I click it and someone walks in front of the TV, the signal dies. If an RPC call drops mid-flight, what actually happens?
Total chaos, honestly. Especially if it's a non-idempotent action. If you call add funds and the connection drops, the client stub just throws a timeout exception. As the developer, you are completely blind.
Oh, wow.
Yeah. Did the network packet die on the way out? Did the server receive it, process it, but then crash before returning the response? Or did the acknowledgement packet just get lost on the way back?
Yeah.
You have absolutely no idea what state the server is actually in.
That is terrifying from a design perspective. It implies you really shouldn't be exposing raw RPC calls over the unpredictable public internet. I mean, it sounds strictly built for back-end-to-back-end communication, where the servers are like sitting in the same secure, highly reliable data center.
That's exactly right. RPC is for tightly coupled internal components where actions and commands are the primary focus.
Yeah.
But if you want to expose the system to massive scale web traffic over the open internet, you have to shift paradigms.
Which brings us to the resource manager. REST, representational state transfer. And the document makes a critical distinction right out of the gate here. REST isn't a strict protocol, it's an architectural style.
Right.
And it flips the RPC script completely. RPC is all about unbounded actions verbs like fire missile or calculate tax. REST restricts you to a strict hierarchy of nouns, named resources.
Right. Things like users, documents, accounts. You address these nouns using URIs, and you interact with them using only a handful of standard HTTP methods.
Post to create, get to read, put to update, delete to remove. So you don't have a customized update user profile action. You just have a user resource, and you fire a delete request at it with the new payload.
Exactly.
It's incredibly rigid. But what really caught my eye in the source are the constraints that make REST scale, specifically statelessness.
Yes. Statelessness is basically the bedrock of the modern web. It dictates that the server keeps absolutely no session state about the client between requests.
None.
None. Every single incoming HTTP request must contain all the context, all the auth tokens, and all the data necessary to process that specific request in total isolation.
Wait, if the server fundamentally refuses to remember me, isn't that a massive waste of bandwidth? Like, I have to reintroduce myself and send my credentials every single time I turn a page on a website. That sounds incredibly inefficient.
It is inefficient on a per-request basis, but you are trading bandwidth overhead for horizontal scalability. Think about the alternative. If a server holds a session state for you, your next request must be routed to that exact same physical machine.
Right.
If millions of users log on, that specific machine gets completely overwhelmed while the others just sit idle.
Oh, I see. Because REST is stateless, I can stick a generic load balancer in front of, say, 10,000 identical server instances.
Exactly. Any server can fulfill any request at any time. If server number 4 catches fire, the load balancer just seamlessly routes your next request to server number 5. You never even notice it happen. It's the ultimate scaling mechanism.
It's a fascinating trade-off. Now, another REST constraint the document highlights is HADOS, hypermedia as the engine of application state. It's a terrible acronym.
It really is a mouthful, yeah.
But it's a really elegant concept. It almost reminds me of a choose-your-own-adventure book dynamically updating itself.
That's a really good way to frame it. How does that look in practice for the client, though?
Well, if I'm building an app that consumes an RPC API, I have to hard code all the logic. I have to know that if the user clicks withdraw, I need to trigger a specific endpoint. But with HADOS, the server dynamically tells the client what moves are legal right now.
Right.
If I fetch a bank account resource, the server sends back the balance, but it also embeds hypermedia links right in the response. Here's the URL to deposit. Here's the URL to withdraw.
And what if that account happens to be overdrawn and frozen?
The server simply doesn't send the withdraw link. The client application doesn't need to understand the complex business logic of why the account is frozen. It just renders whatever links the API hands it. It creates this incredibly resilient, decoupled state machine.
So we have the theoretical landscape laid out. We have RPC, which is lightning fast, action-oriented, and abstracts the network but hates instability.
Yeah.
And we have REST, which is resource-oriented, stateless, highly scalable, and decoupled.
But theory is cheap. Let's look at how these paradigms actually survive in the wild. The document applies all of this to a real-world sandbox, a real-time streaming conversational AI platform. And the constraints here are brutal.
Brutal is an understatement. Imagine you are the engineer tasked with this. The platform demands a total conversational loop budget of under 800 milliseconds.
Less than a single second.
Yeah. That is the time it takes for a user to speak, for the audio to be compressed, sent across the internet to the server, transcribed into text, processed by a massive language model to generate a response, sent to a text-to-speech engine to generate synthesized audio, and streamed all the way back to the user's headphones.
That's insane. To hit an 800 millisecond budget, you clearly can't just dogmatically choose REST or RPC for the entire stack. You have to deploy a mixed protocol paradigm, basically surgically applying each contract where its specific traits solve a physical bottleneck.
Exactly. Let's trace the signal path. It starts at the edge gateway, the entry point where the public user actually hits the system. And the architecture document specifies a strict gateway split here.
Right. For the control plane, which handles session allocation, setting up user profiles, and authentication, they use standard REST.
Which is perfectly aligned with what we just discussed. Authenticating a user and setting up a session profile doesn't require sub-second latency, but it does require handling potentially millions of concurrent user connections.
So REST's statelessness means they can throw massive layer 7 load balancers in front of it and scale out horizontally without any state replication headaches.
Precisely. But then you have the data plane. This is the pipeline handling the actual continuous live audio streaming from the user's microphone. And for this, they completely throw REST out the window.
They have no choice, really. REST relies on HTTP, and HTTP is a request-response protocol that requires a handshake.
And those handshakes are heavy.
Yeah, TCP connection, TLS cryptographic negotiation, exchanging headers. Oh, wait, exchanging all those headers.
Exactly. If you're trying to stream continuous chunks of audio, doing a full HTTP handshake for every single fraction of a second of sound introduces a massive amount of overhead latency. It would blow past that 800 millisecond budget instantly.
So instead of REST, the gateway exposes a public WebSocket API for the data plane. WebSockets allow the client to do that heavy handshake just once. It opens the connection and then leaves the door permanently propped open. You sacrifice the easy, stateless scalability of REST to gain pure, sustained, bidirectional speed. The client just shoves audio frames through that persistent pipeline as fast as possible.
Now the audio is inside the system. It passes the gateway and enters the internal core. The orchestrator service now has to route this audio to the high-throughput text-to-speech engine, and the engineers switch paradigms yet again.
This is where they deploy bidirectional gRPC. So gRPC is Google's modern, high-performance evolution of RPC. But what makes it specifically necessary here? Why not just use more WebSockets internally?
It comes down to serialization and the limitations of modern backend languages. Remember marshalling.
Yeah.
REST and WebSockets typically traffic in JSON, which is text-based. It's great because it's human readable, but for a computer, parsing massive continuous blocks of text-based JSON is incredibly CPU intensive.
And the document points out that many of these orchestrator services run on environments like Node.js, which use a single-threaded event loop. If I understand that correctly, that means the server can only actively process one action at a time in a queue, right?
That's right. It switches between tasks incredibly fast, but it's still just one thread. If you force a single-threaded event loop to stop and parse a heavy JSON payload containing an audio buffer, it literally blocks the thread.
Ouch.
The entire server freezes for a fraction of a second. Doing that repeatedly destroys your throughput.
So gRPC avoids this by using protobufs, or protocol buffers. It's a strictly typed IDL.
Yes. Protobufs don't send text. They compile your data structures down to highly compressed, lightning-fast binary streams.
So the sending server compiles the audio chunk into raw ones and zeros, and the receiving server instantly unmarshals it directly into its memory structures. It completely bypasses that heavy text parsing.
Exactly.
The single thread never blocks. It's tightly integrated back-end-to-back-end communication where network unreliability is near zero. It is the absolute perfect use case for RPC.
But the AI platform doesn't operate entirely within its own safe internal boundaries. Eventually, it has to reach out to external ecosystem boundaries. It uses partner APIs to query external large language models and specialized voice synthesis networks.
And suddenly, we are back out in the wild. We are back on the hostile internet dealing with third-party networks that might experience lag spikes or drop connections.
Not only are they unreliable, but these external LLMs charge per token. They have strict rate limits. If a connection drops and your system blindly retries an expensive inference query, you are literally burning money.
Which brings us full circle back to the first architectural pillar we discussed, idempotency. To survive this ecosystem hop, the AI platform wraps every single external call in idempotent operational wrappers.
They generate a unique request ID for every single turn of the conversation. If the external LLM takes, say, 400 milliseconds too long and the internal timeout triggers, the platform can safely initiate a network-level retry.
Because it knows the LLM provider will recognize the unique ID. The provider's API will say, look, I'm already processing this exact prompt. I'm not going to run it twice and double bill you. It acts as this impenetrable armor against network uncertainty.
It's an incredibly pragmatic architecture. The blueprint doesn't care about theoretical purity at all. It deploys REST for scale, WebSockets for sustained ingestion, gRPC for raw binary throughput, and idempotency for financial safety.
It really reframes how you look at the apps on your phone. The seamless magic of hitting a button and getting an instant result is entirely reliant on this hidden, high-speed choreography. Engineers are constantly balancing the trade-offs of statefulness, latency, and serialization to mask the absolute chaos of the underlying internet.
It's a profound balancing act, and the targets are constantly moving as our demands on the system change.
That's a perfect point, and it ties directly into the provocative thought the design document leaves its engineering team with at the very end. The lead architect poses a question about what to focus on next. Do they double down on internal protobuf optimization, or do they focus heavily on their public WebSocket ingestion streams?
It highlights a massive paradigm shift happening right now in system design.
Exactly. For 20 years, the internet has been dominated by REST. We built a fundamentally stateless web because it was the only way to scale to billions of users. But look at what you and I demand now. We are pushing towards zero-latency AI interactions. We expect fluid, continuous, deeply contextual conversations with machines over audio and video.
And AI inherently requires memory. It requires context. It demands an unbroken stream of stateful data.
So imagine you're an architect looking 5 years into the future. As AI agents become the primary way we interact with the digital world, will the heavy, stateless, transactional overhead of REST eventually become obsolete? Are we witnessing the beginning of a web built not on isolated stateless requests, but entirely on massive, persistent, stateful streams?
It's a fascinating question. If the foundational nature of our traffic changes from distinct clicks to continuous streams, the invisible contracts governing the internet will have to be completely rewritten.
It really makes you wonder. Next time you sit down at a restaurant, just remember, the menu might look incredibly simple, but the kitchen is a war zone, and the only thing keeping your dinner from bursting into flames is a very, very tightly written contract. We'll catch you on the next deep dive.